In the previous two parts, we focused on drift. First, drift in an electric field, followed by drift in an electric field and a magnetic field, and eventually the Hall effect. Also, meanwhile, we discussed our first electronic device, which is a resistor. Okay, now we want to discuss the second type of transport. And this second type of transport is very critical to motion of electrons and holes in diodes, which are very important uh, components, in electronics. This second transport is diffusion. So the first transport, as we said, is drift. The second is diffusion. And diffusion simply means that you have particles in a solution. This solution could be a liquid, or this solution could be gas. You have particles, and the concentration of particles is not uniform. So you have regions where you have higher concentration of particles compared to other regions where you have lower concentrations. So what happens in this case? You get diffusion. Particles diffuse from regions of larger concentrations to regions of smaller concentration. So if we think of a particle density C, that is concentration of particles per unit volume, the flux density of particles, that's if this concentration per unit volume moves with a velocity v, then it creates a flux. And the flux is actually number of particles going through a unit area. And the unit area part comes from unit volume. Okay, so the flux density for a concentration C, or a density of particles C moving with a velocity v, the flux density is CV. And so this flux density, when we say flux, it's moving particles. Okay, this flux density comes from diffusion, from the change in concentrations with position. The change in concentration with position is called gradient of the concentration of particles. Gradient is something to do, a derivative with respect to position. Okay, so in mathematical terms, the flux CV, number of particles per unit area per unit time, because flux meaning also unit time. So area per unit time, per unit area per unit time, is actually equal to the gradient. Gradient is derivative of concentration, change in concentration with position. And this nabla here, we're talking three-dimensional gradients, okay? And maybe in calculus, grad function, or the grad of a function. The grad of a function is actually the gradient, okay? That comes from the gradient. That's a derivative with respect to position. And this nabla, okay, notation nabla, it stands for derivative with respect to position. So nabla is a vector operator, and this vector operator is something like delta by delta x, right? Delta by delta x, that's the operating delta x derivative in the direction I, okay, unit vector I, plus delta by delta y, okay, in the direction j, and delta by delta z, okay, in the remaining direction k, okay, and that's the gradient operator or the grad, okay. So this non-zero gradient, in other words, there is actually a difference in concentration, drives the diffusion flux, okay. And this constant d is a diffusion constant. It changes from one material to another, from a solution to a solution, from a gas to a gas, dependent on the environment in which particles diffuse. So d is called diffusion coefficient, okay, or the diffusion constant. It depends on the medium, on the particle. So this is the equation in 3 dimensions, okay, just to clean it off here. Clean it off. This is the equation in 3 dimensions here for the flux. And the flux is in 3 dimensions, moving in x, y, and z directions. Now, to make things simpler, easier, we're going to focus in only one dimension. So let's talk about change in concentration only along the x direction. So the derivative here is not showing, so I just wrote it. So the flux now in the x direction, flux in the x direction, CVX, which is the concentration of carriers or particles, is equal to minus d and y minus, because the flow is from higher concentration to lower concentration. So it's opposite to the direction of the gradient. So that is why we have a minus sign. Remember, the diffusion is from higher concentration to lower concentration, and the gradient is positive, okay, when we think about it from higher concentration to low concentration. So this minus sign tells me that the flow is opposite to the gradient. So C is concentration. Now, this first slide applies to any solution and to any gas, to any medium. It doesn't have to be a semiconductor. It doesn't have to be electrons and holes. Anything. If you just have, a green paint or a green ink, drop of green ink, you drop it in a cup of water, which is nice, clean water, then this green ink dot would diffuse. You will see it diffusing in the glass container of water, diffusing from this spot all the way, filling up all the glass water. So this is the diffusion. Again, this type of diffusion is governed by this type of equation. So it doesn't have to be a semiconductor. Diffusion is a transport process in any material where you have concentration gradient. But then now let's look at a semiconductor. Let's look at an N-type semiconductor where we have electrons. And let's assume that the electrons have non-uniform concentration in the semiconductor. The free electrons have non-uniform concentration. So in some places, the electrons are more than in some other places. So what do you get? You get diffusion, right? So now we know right from the beginning of this chapter that the current density is always equal to electric charge of the carrier, being electrons in this case, times the density of electrons, N, times the average velocity, Vn. Remember, in this first part, the whole of the first part, we derived Vn for drift when we have an electric field. And that is why we got the mobility and everything. Now, let us think about V when we have diffusion. Where do we get that? You go back here. look at this one here. This is v, the velocity, when it's driven by gradient, when there is diffusion. So CV minus d grad C. So in diffusion, V is actually given as d grad V or grad N or grad C. So in diffusion, the velocity V is not given by mobility like in the drift. It's given by a diffusion coefficient and the gradient of the concentration. So this is what we need to substitute for V, right? And it's exactly, instead of V here, we're going to put Vn, right? Vn or Nv, Nvn, right? Which Nvn is actually our Cv, right? Where C is the concentration, and the concentration in an n-type is N. That's a concentration of free electrons. And V is V sub n, which is the velocity of free electrons. CVn should be replaced by minus d n grad n. So your J will be J equals E, this is E, and this is your N, Vn is simply dn grad n. So this is the diffusion current, or the diffusion current of electrons, in this semiconductor. Similarly, now, where is the minus sign? Look here, there was a minus sign here, right? Where did this minus sign go? This minus sign goes away for the case of electrons because the charge E of the electrons is also negative. So negative with negative, you get positive. So the diffusion current of electrons in an n-type semiconductor is the electronic charge E times dn, where dn is the diffusion coefficient or diffusion constant of electrons, times grad n. Similarly, in a p-type semiconductor, we can talk about the diffusion current density by holes, that's what I'm going to call Jp, is minus E dp. dp is the diffusion coefficient of holes, and P is the concentration of free holes, of course. Okay? So now we have two expressions for diffusion current. Always remember, in semiconductor transport, in semiconductor, how do electrons move? They move either because of drift when you apply an electric field, or you don't have to apply an electric field. You can have motion of electrons and holes in a semiconductor and production of a current density if you have differences in concentration. And that kind of flow or transport, you call it diffusion. Okay, so now here we have the expressions, for the two parts, electron and hole diffusion currents. So now, on the x direction, these operators, nabla, which is a vector operator, now becomes only derivatives along the x direction if everything is confined to the x direction. So my current density, diffusion current density for electrons in an n-type semiconductor is E times diffusion coefficient of electrons times the gradient of electron density, dn by dx. Similarly, the diffusion current for holes in a p-type semiconductor is minus E dp, the diffusion coefficient for holes, dp by dx. Okay? Now, if you want to be fancy, okay, and write, the total current now, let's assume that we have the more general scenario. That is, we have an electric field, but we also have differences in concentration. So we will have the two mechanisms for transport. We will have the drift because of the electric field, as well as the diffusion. So the two together will make the current in a semiconductor. So if you want to write that current in an N-type semiconductor, we call that total current density J sub N, and it has two parts. This first part here is mu N. Okay, so this first part here is the drift part. Remember, comes from the electric field, and this is the same part that we discussed before. And then this part, this is the diffusion part. It comes from the concentration gradient, and this is a three-dimensional equation. Similarly, if we're talking about a p-type, again, here is mu. Again, here is a three-dimensional equation, right, for a current flow, total current flow, current density by holes. And it comes from drift by the electric field, as well as diffusion by the concentration gradients. Okay? Now, to make it easier, and if we think of a one-dimensional semiconductor only along the x-axis, okay, then things are easy in that case. And motion of electrons in an N-type semiconductor along the x-axis only. So here we have the drift part, okay, which is this first part. And here we have the diffusion part for electrons. Similarly, in a p-type semiconductor, here we have the drift part by the electric field, and because of the electric field, and here we have the diffusion part because of gradient. So essentially, what I'm telling you, to move charge carriers, to move electrons and holes in a semiconductor, you need one of two mechanisms. You need drift, you need to apply an electric field, and this electric field will move the carriers, will make them drift. Okay? And because of the environment of the semiconductor, okay, we will have a mobility which dictates, this drift in an electric field. Another mechanism that moves carriers within an electric field is diffusion. And that is if you have differences in carrier concentration in different regions. Okay? And the mechanism that moves carriers in this case is diffusion. And this diffusion is accomplished via gradient of the density of carriers, as well as the diffusion constant of the carriers, which again is affected by the environment, which is the semiconductor itself, right? So actually the semiconductor dictates both the mobility of the carrier in the drift and the diffusion constant, or the diffusion properties of the carrier in the case of the diffusion. So then the question is there any relationships between diffusion coefficient and mobility, since they both relate to the same environment, which is the semiconductor in this case? Okay, before we do that, let me give you some diffusion coefficient values at 300 Kelvin. They actually depend on the temperature. Their values depend on the temperature. And you can see that in a typical semiconductor like germanium, the diffusion coefficient for electrons is 100 centimeters squared per second. And for holes, 49. So holes diffuse at a much lower diffusion coefficient. And normally holes are heavier. So whether they drift or whether they diffuse and drift less readily than electrons. We also saw previously that the mobility of holes is much less than that of electrons. Again, that is because they're heavier. look in silicon, the diffusion coefficient for electrons is 35 at 300 Kelvin, whereas it's only 12 for holes at the same temperature. Similarly, you can see gallium arsenide has a much, much higher diffusion coefficient than both silicon and germanium for electrons, but then it has a very low diffusion coefficient for holes at the same 300 Kelvin. So going back to that question that I posed in the previous slide about what's the relationship, between mobility and diffusion coefficient. And this was worked out, this relationship was worked out by Albert Einstein several years ago in the past century. And he found out that, from the derivation, which I'm not going to do here, he found out that there is a relationship between the mobility of a carrier, electrons or holes, and the diffusion coefficient. He actually found that the diffusion coefficient of electrons in a semiconductor is equal to Kb. Kb is Boltzmann constant, T is temperature, okay? E is electronic charge, times mu n. Mu n is the electron mobility. So there is a relationship between the electron mobility and the diffusion constant of electron in a semiconductor, okay? They are related, they're proportional to one another. Similarly, there is a relationship between the diffusion coefficient of holes and the mobility of holes in the same semiconductor. They are proportional to one another via temperature, okay? And so these are the relationships that connect the two. So here is an example. The whole concentration of silicon at T equals 300 Kelvin is given by this relation. So we have a concentration of holes that depends on X. This is a one-dimensional problem. So problem in one dimension, only the X. And we have variation in concentration. The concentration is not uniform, is not constant throughout. It actually varies exponentially. It decays exponentially with distance, where X is measured in millimeters. If the whole diffusion coefficient is 48 centimeters squared second minus 1, okay, determine the whole diffusion current as a function of X. So what's the diffusion current from holes in this? So we don't have any electric field applied. We just have this piece of a p-type semiconductor, which has gradient in the concentration of holes, and we want to figure out the diffusion current coming from these holes. So this is P here. So what we need is JPX, that's the diffusion current density from holes, is related to dP by dx. So we have to get the gradient or the derivative of P with respect to X. And then we have to plug in the diffusion coefficient of holes and then the electronic charge of holes. So let's start by getting dP. dP is actually this part here, dP by dx. So if you go back, and this is not a calculus class, just differentiate this. This is a simple exponential. Take dP by dx, you will find that you will have minus 1 over 22.5 times 10 to 18 times exponential this amount here, which is this part. This is dP by dx. Okay, very straightforward. You can show that this is true. So this is your derivative. So you put your derivative there. This is your d. Okay, and this is your electronic charge E. Okay, so once you substitute those, you get JPX equals 3.41 times 10 to minus 4 exponential minus x over 22.5. And look, it is Coulomb per centimeter squared per second. Remember, Coulomb per second is ampere. So it's ampere per centimeter squared, which is a current density. The current density is current per unit volume. Okay, so that is the diffusion current density. One last thing is, if we have a semiconductor and it's isolated from everything around it, it's given a certain temperature and isolated, so there is no electric field applied, right, in this semiconductor, isolated from everything. What happens, inside this semiconductor? If it's isolated and no electric field, there will be some motion of charge carriers at the beginning, but immediately this motion comes to zero because we reach equilibrium, right? This motion at the beginning is because of diffusion. Carriers, they start diffusing from one place to another and then move randomly. And then after a little bit, very, very short time, everything is settled and we reach equilibrium. So when we reach equilibrium, the total current density is zero. Let's assume we have an N-type semiconductor. So the drift current and the current that comes from diffusion is zero. Okay, and so this relationship is true. The other thing is, the electric field can be written as this electric field is a kind of an internal electric field. There is no external electric field applied. So what happens is, if you have an isolated semiconductor, you have internal electric field, and then you have internal changes or gradients in concentration. So because of this, you have drift and you have diffusion, and then after a little bit equilibrium, you get zero net current, right? The internal electric field comes from the energy of the carriers in the semiconductor. So it comes from the energy of the electrons, the thermal motion of the electrons inside the semiconductor. And the electric field, okay, E times E, or the electric force, is equal to, actually, the electric field is, from Poisson equation, is actually the gradient of the potential. That is Poisson equation, if you like. Okay. Now, if we multiply both sides by E, we get this relationship. Okay, which is here. Okay, a relationship between E times E minus delta EV. Why am I using E, small e times capital E? Because I want to substitute it for this product here, E times E. Okay, so it's equal to E times V. V is potential. Potential is energy per unit charge, right? Now, if I multiply it by E, then that's the energy in the electron. So that's the total energy in an electron in a semiconductor. This total energy in an electron in a semiconductor, okay, the gradient of this, that's the derivative of this total energy of a semiconductor, of an electron in a semiconductor, can be written as, in one dimension, can be written as the derivative with respect to x of a typical energy of an electron in a semiconductor, which is the energy at mid-cap, or at the intrinsic Fermi level. The intrinsic Fermi level energy is a representative energy of, or an average energy, if you like, quote unquote, of an electron in a semiconductor. So this gradient of an energy of an electron in a semiconductor is written as, can be written as dEI by dx. EI is the intrinsic Fermi level. Okay, so this E times capital E can be substituted by the position derivative of the intrinsic Fermi level. Now, this minus sign is no longer there, because once you have an electron charge Okay, the electron charge is negative, and so if I drop the sign of the charge, then the equation simply becomes small e times capital E equals to the derivative of the intrinsic Fermi level with respect to x. So I'm going to take this and put it back in this equilibrium equation up here. So instead of small e times capital E, I'll put dEI by dx. Okay? And then I'll bring to your attention N. In this N-type semiconductor, N, the concentration of free carriers, we did this back in chapter 4, can be written in this form. So we can write dN by dx. Why do I need dN by dx? Because I have it here in this part. So I'm going to get that from the equilibrium, because this equation is valid at equilibrium. So I'm going to get dN by dx from the equilibrium carrier concentration, which is this one here. So if I differentiate dN by dx, then you can immediately see that the derivative is here. And then if you organize it, you get dN by dx equals to N kb over T dEf by dx minus dEi by dx. Now, this EF here is the Fermi energy in the N-type semiconductor. Remember, this EI is the Fermi energy in the intrinsic semiconductor. Okay? So, if you substitute this for dN dx, and if you substitute this for small e, small capital E, in this equation, and reorganize the equation, you immediately arrive at this result. This result simply tells us that the gradient of the Fermi level in an N-type semiconductor is equal to 0 in thermal equilibrium, in thermodynamic equilibrium. This is very important. So in equilibrium, because you have 0 net current density, that means your Fermi level in the semiconductor, its gradient is equal to 0. Gradient is equal to 0, meaning that the slope of the Fermi level is 0. The slope of the Fermi level is 0 along the x direction, means that the angle that the Fermi level line makes with the x direction is 0. In other words, the Fermi level in a semiconductor in equilibrium, it stays flat, completely horizontal, parallel to the x-axis, as long as the semiconductor is in equilibrium. So for a semiconductor in equilibrium, in thermal equilibrium or thermodynamic equilibrium, the Fermi level is flat, is always parallel to the x-axis. That's when we're talking about only variations along the x-axis, and when we're talking about a one-dimensional problem. So in thermal equilibrium, the Fermi level of a semiconductor is always